Alright, so today we are continuing on with our talk of applications of filtrations on standard groups. Might be a bit of a shorter one because next time we are moving on to Bourbaki's treatment of Lie groups, and so we're going to be, it's going to take some filtering through the text in that to check for any repeat information, so hopefully we can just kind of take it easy with this one. It'd be better to do that as a separate video. So anyways, so for our setup for today, we're going to let K be a locally compact ultrametric field with valuation ring A, which itself has a maximal ideal M. We'll let P be the character of our base field, and Q the cardinality of its residue field. And also, no, we're not done yet. W be the canonical valuation from K to an integer or infinity, with the valuation of a non-zero element of K, the image of the valuations of non-zero elements of K, forming the entire integers. Then the canonical absolute value on K is defined equivalently as follows. First off, the absolute value of x is going to be the inverse of the cardinality of the valuation ring A over x times A. So that's for all Lx in our valuation ring, of course. I guess these are equivalent definitions. We have that the absolute value of x is equal to q to the negative valuation of x for all x in our base field. And third, multiplication by x alters the Haar measure on K by the absolute value. Now suppose R is relatively prime to P, and we consider fr sending A star to A star. Let S being, of course, the cardinality of the kernel of FR be the number of roots of unity in K with exponent dividing R. This justifies a theorem where the cardinality of A star over A star to the R is equal to the absolute value of R to the -1 times S. And we get this by a consequence of a more general theorem of vanilla groups over K. We're going to let G be a commutative, compact, analytic group over K, and we're going to define HR of G to be the cardinality of the co-kernel of FR over the cardinality of the kernel of FR. We will see the right-hand side is well defined, that is the numerator. Both numbers are finite, and we will compute it. So we're going to let n be the k dimension of G. Okay, and then this brings us to our next theorem, which we're going to use as a step, where HR states that HR of G is well defined and is equal to the absolute value of R to the -n. Alright, so I'm going to write this in a different way than in the book, which is going to make it difficult. So our first step is that the theorem is true for G if G contains a normal group submanifold H such that the theorem holds for H and G over H. So essentially we can like factor out this theorem through a quotient. Now, so we consider the commutative diagram with exact rows. One going into H, going into G, going into G over H, going into 1. And we have that same exact sequence again, exact in both terms, no pun intended. And then we have 3 morphisms. We're going to call them phi1 here, call them phi1, phi2, phi3. But just to make our notation easier, but phi1 is going to be fr on A, is going to be fr. Note with each phi equal to fr on the appropriate domain. Then I think this is an old like category theory. Isn't this like the 5 lemma or something? The 5 theorem? It's something weird like that. I think this is what that is. We get from this that there exists an exact sequence from our 5 theorem. I think it is. It's going to give us the exact sequence of 1 into the kernel of phi1 into the kernel of phi2 into the kernel of phi3 into the co-kernel of phi1 into the co-kernel of phi2. It's 5 theorem. Five lemma. Co-kernel phi3, then into 1. And this map from the kernel of delta 3 to the co-kernel of delta 1 we call phi1, sorry, we call delta. It's the 5 lemma. I don't know if this is it. It looks like it. 1 sec, sorry, I'm getting a little distracted here. I think this is the 5 lemma. I'd like someone to verify, but it seems like that. Now, most of these maps are defined pretty obviously. The only tricky one is delta, so we define delta as follows. I'm going to let x double prime be in the kernel of v3 and choose x in G such that x maps, such that it maps to x double prime mod h. Then, of course, if k double prime's in the kernel of v3 implies that x to the r lies within h. So we define delta of x prime double prime to be the the image of XR in the co-kernel of phi1. And you can verify that this is well defined, so it doesn't matter what representative x we choose for x double prime, and that our sequence is then exact. Now, as our theorem is true by assumption for h and g over h, then the kernel of phi1, the kernel of phi3, the co-kernel of phi1, and the co-kernel of phi3 are finite. Which is going to make the kernel and co-kernel of phi2 are finite by exactness. Then we also have from this that 1 is the cardinality of the kernel of phi1 times the cardinality of the kernel of phi2 inverse times the cardinality of phi3 times the cardinality of the co-kernel of phi1 inverse times the cardinality of the co-kernel of phi2 times the cardinality of the co-kernel of phi3 inverse. So HR of G, which you recall, is the size of the co-kernel divided by the size of the kernel, is going to be HR of H times HR of G over H. So for an explicit formula, we're going to let M be the k-dimension of H. So the k-dimension of G over H is n minus M. And then R, the absolute value of R to the negative n is the absolute value of R to the negative m times the absolute value of R to the m minus n. Since by hypothesis HR of H is R to the negative m, and HR of G over H is m minus n. HR of G is the absolute value of R to the negative n, as we wanted. Now we need our second part, which is that the theorem is true for G if it is a finite group. Oops, sorry. One second. The way they have this set up, I kind of got to bounce back and forth between a couple different distinct areas of the book, and sometimes it takes a second. And so, did we just jump to the proof? Yeah. So the proof for this one, we have an exact sequence from 1 to the kernel of fr to g to g to the co-kernel of fr to 1. Since g is finite, the kernel of fr and the co-kernel of fr are finite, n equals 0. We have first off that 1 is the cardinality of the co-kernel of fr times the co-kernel of g inverse times the norm, the size. The cardinality is the right term in this context. G inverse cardinality of g, the cardinality of the kernel of fr inverse. These terms in the middle cancel out, and so we're left with hr of g, which gives that 1 is r to the negative n. And part 3, finally, is the theorem is true of G being H lambda when H is a standard group and lambda is sufficiently bigger than 0. Let's go over to that page. So we're going to let lambda be large enough that f sub r of g lambda to g of lambda plus w of r is an isomorphism. Then we have that the cardinality of the kernel of f to the r is 1, and the cardinality of the co-kernel of f sub r is q to the valuation of r to the n, which is just the absolute value of r to the negative n. And with that, we have a bit of a ways to go in SARE yet, but I feel like we want to make sure we don't get too far ahead in one versus the other. So we're going to be switching over to Bourbaki here. Next up, yeah. So yeah, I think a lot of it might be duplicates, but I think it'll be good to review this stuff anyways, so yeah. Thanks for watching.